So today we are going to talk about the third equation in the conservation laws, which is the energy equation. In previous classes or sessions, we did cover the derivation of the continuity equation and the momentum equation. This is the third and the last conservation law that we need to use to jump into the solving fluid flow problem, considering both the hydrodynamics and the thermal aspects. And this is where the energy equation it's becoming the end. So what's energy equation? What's the conservation laws? If we talk in a scalar situation, everyone is familiar with the first law of thermodynamics, right? So the first law of thermodynamics is simply the conservation law in the scalar quantity. So that's the first law of thermodynamics. And remember, we are talking about control volume system. So in thermodynamics, we have either a control mass system, which we sometimes call it the closed system, and the control volume system, which is known also as the open system, where the system boundaries are penetrated by mass flow rate in and out. So if you recall that first law of thermodynamics for the open system, you recall the equation is summation of Q dot plus summation of W dot should equal to the change in the mass flow rate times the change of enthalpy plus the change in the kinetic energy plus the change in the potential energy, or it's keep that potential energy here, right? Which is simply mg delta z, right? That's the potential energy change, in addition to the change of the energy of the control volume itself relative to the time t. So this is the unsteady first law thermodynamic equation for open system, or is a system that has mass flow rate into it. So this is the equation, right? So if we want to identify each term, I can go and say that the first term here is presenting the heat transfer. It's maybe this color is not helping here, so let me get a darker color. So this is the heat transfer, and this is the work. And these two are actually happening through the boundary, through the control volume boundaries. So this is my control volume. That control volume has initial content of energy, and because of the exchanging energy with the surrounding here through the mass flow rate in and out, and also the heat transfer could be in or out, and the work that could be in and out. And we give the dot because that's everything related to the time. This is mass dot, this is mass dot here. And each one of these fluids in and out, it carries certain quantity of energy that can be presented by the different terms here. So again, the total heat transfer and work that going through the boundary of the control volume should equal to the energy change by fluid flow in and out. So this big term here, I think that guy is staying out. So let me see this. So this term is presenting the energy change or it's the energy change due to fluid flow. So this is the different forms of energy carried by that fluid in and out the system, okay? And we know that H is the enthalpy, and V is the velocity, and Z is the altitude or the position. And in simple language, this is presenting my potential energy. Velocity is indicating my kinetic energy. And we know that enthalpy is a combination of the internal energy plus what we call the flow energy. So these are the different forms of energy carried by a fluid of each one of these fluid lines, in or out. Then this term, the last term here, is presenting the change internally inside that control volume. So this is actually the energy change within the control volume. So this Q and W and the mass flow rate, all of them are crossing the boundaries of the control volume. So due to the in and out for each one of these terms, it will change the final content of the energy inside the control volume. So you start with a control volume carrying certain quantity of energy, then you start exchanging energy in and out to that control volume, either directly by the heat or the work or carried by the fluid coming in and out. Then after a certain period of time, you would say, okay, I'm going to look into what is the content of the energy of my control volume right now. The change of that content of the control volume energy inside relative to the time that's presented by this term here. So if I would like to write the general equation here, I would say the following. The general description of the energy balance equation is the temporal change of control volume, I mean inside that control volume, right, should equal to summation of energy carried by fluid going in or out that control volume plus energy in summation transport in or out the control volume. So that the temporal change, this is, as I said, this is will be the internal, and it's mainly the internal energy. That's what's going to change inside the control volume. Energy carried by the fluid, that's going to be the enthalpy, kinetic energy, and potential energy if it's actually exists. But since I'm talking about the flow of the fluid, maybe potential energy is not going to be considered that much. And the energy transport in or out the control volume, I mean here by the heat plus work So I'm going to add another term here for the work, which is summation of the work done on or by the control volume. And that work could be due to surface force or body forces. Let's keep that term only for the heat, and the heat is going to be mainly by either conduction or radiation. And let's keep that work is by itself as a standalone term here. So the energy carried in and out by the mass, which is enthalpy and kinetic energy, in addition to the energy transport by conduction or radiation to the control volume. So that's simply presenting the Q, right? Dot. This is presenting the W dot, and this is presenting the D delta M dot multiplied by the different forms of energy, that term up here. and this will equal this term representing dE by dt. So this is just a generic format for the energy equation, and we need to know now how we can calculate each one of them. So this is dE by dt, and remember, this is within the control volume. This term here is going to presenting the energy change by the mass. We're going to call that actually dE dot. This is the total energy exchanged by the transport of the mass. Then by conduction, we're going to call that dQ dot. By radiation, I think I missed the N here. Heat transfer by radiation, we're going to give that actually dQ dot S. And then we're going to call that work done by the surface force, right? This is surface force or body force. We know that force, time distances give us work. That's how we classify this. And if you go back to the momentum equation derivation, we also classify the forces into surface force and gravity force. So we're going to call that surface force here dA dot. And we're going to call that body force as coefficient K times that velocity. So, and usually this term is neglected like what we did before in the momentum equation. So now what we need to do is to start actually giving an individual expression for each one of these quantities. Then we will combine everything together to get into the energy equation. So that's what I'm going to do now. I'm going to drive standalone expression for each one of these terms. So if I start with the what energy we have within the control volume, I'll call that number 1. So that's 1. The energy within the control volume in a simple language, it's going to be internal. And maybe sometimes we have that's internal energy. And sometimes we may have kinetic energy. So if your system is large enough, maybe the velocity would be considered inside that control volume. So how we calculate the internal energy? Internal energy, we're going to give the actually internal energy is simply defined by E times M. So M is the mass of the control volume, and E is the specific internal energy. The mass is given by kilogram, and the specific internal energy is kilojoule per kilogram. And we know that when I say specific internal energy, specific enthalpy, specific entropy, and that's all indicating per unit mass. The word is specific for this specific thermophysical property is indicating the property per unit mass. What about kinetic energy? It's simply half mv squared. So I can replace the mass by multiplying rho times the v. What is v actually is the volume of the control volume, and rho is the density of fluid inside the control volume. We know that volume is given by meter cube as units, and the density is kilogram per meter cube. So that's will give me the mass. So I can write the equation for the E of the control volume as following. It's rho V, that's the mass, times E, that give me the internal energy, plus half rho V, this is presenting the mass, times the velocity squared. So if I pick up a fluid element, that's a standard that we used in the continuity and the momentum equation, I'm going to have a cubical shape control volume here. That's my element, fluid element. Okay, so if I give that direction x, this is y, and this is z. So the dx is a side length in the x direction, dy is a side length in the y direction, and dz is a side length in the z direction. So I can simply actually replace the volume of the element by dx, dy, and dz. So I can write down the energy inside that control volume can be written as rho E dx, dy, dz plus half rho, and the volume here is going to be dx, dy, dz, and we have the volume square. Remember, sorry, that's a velocity. Remember, we have the velocity in the form of a vector, right? So I would call it like v squared for now. So I can rewrite that equation. I can take dx, dy, dz as a common factor. So I will have the energy within that controlled volume is equal to rho E plus v squared divided by 2 dx, dy, and dz. So now if I want to get the variation relative to the time, so partial E of that control volume by partial time t will be the derivative relative to the time of that rho E plus v squared divided by 2 dx, dy, dz, right? Dx, dy, dz is not going to change. These are the dimension. The control volume we are using here has a fixed dimension, so dx, dy, dz is not going to change with time, but everything else would be changed with time. So this is the first term that we can drive into the general equation. So this is the dE by dt, which happening within the control volume. The second term that I would like to go is actually the term dE, which is the energy carried by the fluid in and out through the boundaries of that control volume. So I would like to drive that term next. Remember, we're still dealing with the control volume of a cubical shape, right? It's always good to have that element next to you so you can actually there's the x-axis, y-axis, and this is z. There's dx, dy, and dz. Now, I will pick only one face or one direction. So I'm going to look to the x direction here. Then using similarity, we can do actually the y and z. So we have a mass flow rate coming through the back face of that control volume. I'm going to call that m dot in. Then I know that there is a mass is going to leave that face here. That's m dot out. How we calculate the mass flow rate? Remember, mass flow rate is simply rho times A times the velocity. And since A, that's my flow area, right? Times the velocity in that direction. So if I want to calculate the mass flow rate in the x direction, so m dot n in the x direction should equal to rho times the velocity in the x direction is going to be u multiplied by the flow area, which is actually going to be dy times dz. That's the mass flow rate. But I know that the mass flow rate, that mass, quantity of mass, will carry certain energy, and this energy will be simply the internal energy carried by that fluid and the kinetic energy as well. So if I want to get the energy in with this mass flow rate in the x direction, will be simply you multiply the mass. If I talk about scalar value, I'm going to multiply that by E plus Vn squared over 2. This will give me the carried internal energy by the fluid in addition to the carried kinetic energy of that flow. So I'm going to write down that here. That's rho u, right? Then I will multiply by E plus the velocity in is simply V squared over 2 multiplied by dy dt. So this is the energy coming in the x direction. Now, if you use Taylor series, you can simply show that if this is a mass flow rate in, there is mass flow rate out, and the mass flow rate out is related to the mass flow rate in by plus or minus value, right? So if you have a 5 kilogram per second coming in, whatever the number that's coming out, right? If it's coming out 7, it can be expressed as 5 plus 2. And if it's coming out 3, it's 5 minus 2. Why I'm saying here that the mass flow rate out is simply the same quantity of mass flow rate in addition to the variation of that mass flow rate in the x direction. So in a simple language here, the energy out in the x direction should equal to let's write down that here. So the mass flow rate out should equal the mass flow rate in plus the variation of the mass flow rate relative to the x in the x direction. So if the mass flow rate in is simply rho u dy by dz, this should be partial rho u dz dy by partial x dx. So this will be rho u dy dz plus this term here. I'm taking derivative for density velocity times dy dz. dy dz is not going to change with x. So I'm going to end up having here partial rho u by partial x dx dy dz. So this is the mass flow rate out, right? So if I want to get the energy out of this mass flow rate out, I'm going to multiply that by the same content of the energy, which is the internal energy and the kinetic energy. So this equation will be, in a simple language here, is going to be rho u times E plus V squared over 2 dy dz plus this will be E plus V squared over 2 times partial rho u by partial x times dy dz dx. This is the total energy exit from that cubical shape into the x direction. So if I want to get the net energy between the in and out, so if I get the change in the energy in the x direction should be the difference in between. So if you get the difference in between, you'll find this term will cancel out. I will get this term in a negative value. So I will end up having minus partial. Remember, that mass has to be multiplied by the energy. So this should be inside the derivative here. So I will have that partial by partial x rho u multiplied by E plus V squared over 2. I'm going to put this totally in a bracket here. Then I will have dy dx here, dy dz dx. And the negative because I'm subtracting what's in minus what's out. So this is the change, which we can call that actually dE dot. But remember, this is only in the x direction. If I want to get dE dot in all directions, it's going to be simply dE dot total will equal to, it seems to be that I will have dy dx dz is common factor. So I will have minus also as a common factor, partial rho u times E plus V squared over 2 by partial x. Remember, you have this totally in bracket plus partial. I will open a bracket here. That's rho v multiplied by E plus V squared over 2. Remember, we deal with velocity as a vector. This is by partial y plus partial bracket parentheses rho w times E plus velocity vector squared divided by 2. This is relative to the z. Then this is dx, dy, and dz. Then I'm going to frame this as my second term. So I'm going to call that number 2. And we're going to call this number 1. Remember, we're still looking for the different pieces for this equation. So I got that term, then I get this term. Now I would like to get the heat transfer by conduction. I want to involve the radiation and any internal heat source in addition to the work done by the different forces to complete that energy equation. It's quite too much math in here, but it's good to be aware of how this equation was derived. So number 3, one was actually the energy in the control volume. This is number 2. This is actually dE dot. That's what we are looking for. Number 3, I'm going to look to the heat transfer. We all know that Fourier's law for conduction. So Q is equal minus lambda A partial T by partial X, whereas lambda is the thermal conductivity. A, this is watt per meter Kelvin. A is the area perpendicular to the heat transfer. So that's the area. That's in meter square. And partial T by partial X is the temperature gradient of the in the direction of heat transfer. And that's why we have negative, because as heat goes in one direction, the temperature is going down, because this is a driving force. So this is the equation that I can get this Q that's going into that phase in the X direction. So if I want to get the outlet heat, very similar to what we did with the mass flow rate. So Q out in the X direction should equal the same heat in plus the variation of that heat in relative to the X direction times dx. So this is Q in the X, this is Q out in the X. I can get the difference in between. So dq dot in the X direction will equal Q in the X direction minus Q out in the X direction. These two terms will cancel out. This negative comes out, and because I do the negative sign, so it's going to be actually plus. So I'm going to end up having plus. Then I will have this term here, which is partial by partial X lambda partial T by partial X. If I look to the area, if the heat is coming in this way, this is your Qn. The area is going to be dy dz, right? So if the area here is dy dz, that's not going to change with x. So there will be dy dz outside, and there's originally dx. So I will have dy dz dx. This is dq dot in the x direction. If you want to get dq dot in the whole control volume in all directions, I will have partial by partial x lambda partial t by partial x plus partial by partial y lambda partial t partial y plus partial by partial z for lambda partial t by partial z. And now I'm collecting dy dz dx as a common factor. I'm going to frame this, and I'm going to call that number, I guess it's number 3, right? We get 1 for dE control volume. Number 2 was for the energy carried by the mass. And number 3 will be the heat transfer by conduction here. So radiation is usually neglected. So remember, that term here would be actually, I would say radiation plus internal heat source. Right? So radiation is, in most cases, will be neglected. So this is going to present mainly the internal heat source. So that doesn't need any derivation here. So the major part that we need to work with is actually the work, which is part number 4. And the work need force times distance. And the force is classified under surface force and body force. So that's the little bit most stressful piece of derivation that we need to do. So let's see how we can actually derive a formula for the work based on the surface and the body forces here. I will start with the surface. So let's drive the part A, which is work due to surface force. So we classify the surface force like what we did before with the momentum equation derivation. It could be a pressure, could be due to normal stress, and number 3 is due to shear stress. When I say normal stress or shear stress, it's the force coming from that stress. So it's actually normal force developed due to normal stress. I mean, normal stress here is compression or expansion. And number 2 is the shear stress that coming from the normal force. Actually, it's not going to be normal, it's going to be the parallel force developed due to shear stress. So we would like to drive a formula for each one of the 3 here. That's pressure. So I would say this is forces, normal forces, or force developed due to, I would say, hydrostatic pressure. If you pick that fluid element somewhere deep inside a fluid flow, the altitude or the depth of that fluid element will cause a hydrostatic force. So let's derive the work formula due to the pressure force. So I would say that's number 1, work due to pressure. That's one type of the surface forces, right? So we know that work is force times distance. But we also know that everything in the original equation is relative to the time, right? So we are trying to write everything relative to the time. So we would like to get that divided by the time. And this will lead us to be force times distance over time. That's a velocity. So you can get the same work rate by multiplying force times velocity. And we know that force can be calculated from the pressure times the area. So this is just a simple scalar way to show you how the pressure is related to the work, right? So that's what we're going to do right now. So I'm going to take the, remember we call the surface force in the original is dA dot. I'm going to call that in the x direction. So it will be actually the pressure. Again, let's draw the fluid element. Visualization is always good to display for the audience. Again, this is the x direction, this is y, this is z, this is dx, it's dy, it's dz, and we're looking for the pressure in that back face. And there's also a pressure over that face, right? So the pressure times the area will give me a force, and there's a velocity in that direction for the fluid. So that's how the work will come out. So this will be P, that's a pressure, times the area, which is dy dz, times the velocity in this direction, which is u, right? Then this is the surface force in that direction. If you're going to get the surface force in that direction, it will be the same as this. Plus the variation of that force. That's a P, U, dy, dz relative to the x dx. Very similar to what we did with the mass flow rate and with the conduction heat transfer. So in this case, you'll find this term will cancel out. I will end up having minus partial PU by partial x, and y and z is not relative to the x, is going to be constant, is going to get out, so I will have dx dy dz. So I can say that dA dot in all direction can be written as minus common factor partial PU by partial x plus partial PV by partial y plus partial PW by partial z, and I have the dx dy dz as a common factor. So that's the first type of work came from the pressure. Now let's get that due to the normal stress. Due to normal stress. We all know that stress is equal actually force over area. So I can get the force from the stress, and when I get the force, I will multiply by the velocity, I will get the work. So you will find that dA dot in the x will be simply minus partial sigma xx, this is the normal stress in the x direction, times the area, which is dy dz, times the velocity u. You change that relative to the x. It is the same way. You end up having this term in the x direction. I got the same term in the x direction. So I can write dA dot in all direction is going to be minus partial sigma xx times u by partial x plus sigma yy, change of sigma yy times v divided by partial y plus partial sigma zz times w by partial z, and I will have dx dy dz as a common factor. So this is the work component due to the normal stress for that fluid element. The last one will be actually the shear stress. So let's now calculate the work due to the force generated by the shear stress. So let's draw the fluid element again. So this is the x-axis in this way, y-axis in this way, z-axis in this way. So for each phase, that's number 3, work due to shear stress. Now, for each phase, we don't have only one shear stress. So for each phase, we used to have one normal stress, right? So if I look to that phase, I have sigma x that way. It's one normal stress over that phase. But if I look to this phase, I would have actually 2 shear stress. And the shear stress usually given by tau, and tau has 2 components to read the tau, right? So the first one is the shear stress perpendicular to and be in the direction of. So this phase here is perpendicular to the x-axis, right? So I would have 2 shear stresses here. I would have one going this way, and I would have one going this way. This is tau perpendicular to the x in the y direction. And I would have this tau perpendicular to the x in the z direction. If I pick the upper phase here, I will have one normal force or normal stress, sigma z, right? And sometimes we call that sigma xx, and this is sigma zz. Now I would have 2 shear forces into that direction. I would have this one, which is tau perpendicular to the z in the x direction, and I would have one in that direction, that's tau z in the y direction. And everyone knows that tau xz is equal tau zx, right? So for each phase now I have multiple shear forces, right? So if I look to the final effect of the shear stress, dA dot, just on the x direction, right? So when I say that I have tau xy, so now I'm perpendicular to the x in the y direction, this guy. So the area parallel to that shear stress is the dy dz. So I'm going to multiply by dy dz. Remember, the velocity in the y direction, this is in the y direction according to the labeling system. If you are in the y direction, you will have the velocity component v, right? So this is 1. Then if I look to the variation of this one, it will be the same. Tau xy times v times dy dz plus whatever the variation, tau xy v by partial x. Then I would have dy dz out, and there's dx in addition to that. So if you simplify that, you end up having dA dot in the x direction. That's only for one component, right? I should add the other one now. So I have tau xz, which is this one. That's going into the z direction. So I'm going to multiply that by w. And the area parallel to that shear stress is dy dz minus same one plus whatever the change that would happen in this term. Now the variation is going into the x. I'm looking for everything in the x direction. And here I will have dy dz and dx as well. So now, instead of having only one component, I have the two components on that face here. So now if I simplify, these terms will cancel out. I will end up having the following here. Dy dx dz is common factor. I'll take the minus also out. I will have partial tau x y times v by partial x plus partial tau x z times w by partial x, and I will have dx dy dz as a common factor. That's only in the x direction, right? Then you can add the one for the y, one for the z as well. So I have 6 components, right? They will look like the following here. dA dot all will be minus partial tau x y v by partial x plus partial tau x z w by partial x. Then I will have plus partial tau x y. I got xy, so I'll have yx. So that's in the x direction, so it's going to be multiplied by u, and that's going to be by partial y plus partial zx tau zx vx. Again, it's perpendicular to the z in the x direction, so I will have u, and this will change by z. Then I will have partial tau xz, that's times w relative to the x, plus partial tau, I should have yz times omega divided by partial y. So 2 components of u, I should have one that's in the, that's omega. So I have xz, I repeated this one. That should be, I have xy, yx, xz, zx, I have yz, so this should be actually zy, and this should be in the v direction, v velocity here, because in the direction of y. So this is tau vy times v divided by, that should be partial y. Actually, partial z, right? It's y, oh, it's partial z. So the derivative for the first letter and the velocity for the second letter. So let me write that again in a clear way. I have partial tau xy. It's the variation in the x, and the velocity component is v, plus partial tau xz. This will be partial x times w. So I got xy, xz. The third one will be yz. So it's variation relative to the y and multiplied by omega because in the direction of z, plus you flip xy to becomes yx, xz becomes zx, and yz becomes zy. So this will be partial yx tau yx. This will be partial y, but u because in the direction of x, plus partial, I will flip this tau zx. It's going to be by partial z, and in the direction of x, so it's going to be u, plus I'll flip that, so we got xy, yx, xz, zx, yz. It will be partial tau zy. This will be by partial z and times v. So I should have now two derivatives relative to the x, two to the y, two to the z, two with the u component, two with the v component, and two with the w component, and dx, dy, dz should be outside here. So this is dA dot for all of them due to the shear. Now you need to combine the one relative to the shear with the one coming from the normal stress and the one that's coming from the pressure. This will only give you the work done by surface force, all the surface forces in all directions. So to do that, you should end up having a combination of all of them. So I will have d a dot, that's the total work done due to surface force in all directions. So you will have the following equation. I would have these three terms here. So I would have minus partial pu by partial x plus partial pv by partial y plus partial pw by partial z. That's now the work due to pressure. So that's term is pressure. I should multiply by dx, dy, dz, but I'm going to keep that term as a common factor for all of them at the end. So now going to the second term, that's due to the normal stress. I'm going to add all of them. The negative is out already, so I will have plus partial sigma xxu by partial x plus partial sigma yy v by partial y plus partial sigma zz w by partial z. And this is the work done due to the normal stress. I still should have dx, dy, dz outside. I'm going to keep it for now. Then I'm going to go for that big term that came from the shear stress, 6 components. So I will add up plus. The negative is already taken out. Then you're going to list all of these again. So I will have, let's keep x, y, z next to each other. So I will have, it's hard, it's 2 by 2. So it will be, let me start with the, relative x first. Partial tau xy. This is relative to the x in the y direction, so it's going to be v plus partial tau xz. This will be relative to the x and the velocity in the z direction, plus let's take the y, it's partial tau yx. So it's going to be partial y, and it's going to be u plus partial tau yz. It's going to be by partial y. It's going to be w plus partial, the last two is tau xz and tau z It's going to be Zx, and Zy. This will be by partial Z in U velocity here. This will be by partial Z times V velocity here. And this is totally multiplied by dx, dy, dz. And what number this equation should be? That should be number 4. Number 1 was the dE control volume by dt. Number 2 was the dE dot. Number 3 was for the heat transfer, and number 4 now for the surface force. Okay. And simply body force will be the gravity, right? So, and usually would be neglected. So this is now all the pieces that we need to go back into this equation. We calculate this is equation 1. This came from equation 2. That's equation 3. That's equation 4. Then body force, it's defined by the body force here is mostly electric or magnetic because the gravity is not really having that impact. So that's actually the coefficient that determine the magnetic or electric field time velocity to give you the body force. Again, this will be also neglected most of the time. So at least we have the 4 major components of this equation. Let's add all of them together and see how the equation will look like. So keep in mind, the equation was dE by dt over that control volume should equal to the dE dot plus dQ dot plus dA dot plus the heat source plus the body force work. Okay, so that's the body force work. Again, could be electric, magnetic, or gravity. Most of the time, all of them are neglected. This is internal heat source. Could be as radiation as well. But again, it's most of the cases, it's also radiation is neglected, but heat source is not. So let's keep it as common factor here. Then this is the work due to surface force. We got pressure, normal stress, and shear stress. And this is the conduction, heat transfer, and this is the change of energy due to mass transfer, and this is the time change of control volume energy. So if we collect the pieces, I should end up having the following equation here. Partial by partial T rho E plus V squared over 2 equal to minus partial rho U E plus V squared over 2 by partial X plus partial rho V E plus V squared over 2 by partial Y plus partial rho W E plus V squared over 2 by partial Z plus, let's close that term here. So this term is the dE dot plus that conduction term came to be partial by partial X lambda partial T by partial X plus partial by partial Y lambda partial T by partial Y plus partial by partial Z lambda partial T partial Z. That's the conduction term. Then I'm going to add all that term here again for the surface forces. So this will be plus minus partial PU by partial X plus partial PV by partial Y plus partial PW by partial Z plus partial sigma XXU by partial X plus partial sigma YYV by partial Y plus partial sigma ZZ W by partial Z plus the 6 terms for the shear stress. So this will be partial tau XY V by partial X plus partial tau XZ times W by partial X plus partial tau YX, that's U by partial Y, plus I will just keep the shear stress element or component in here. Partial number 4 is tau YZ, partial tau YZ, so that's by partial Y times W plus partial tau VX, that's going to be U by partial Z plus partial tau VY, that's going to be V and relative to the Z. Okay, so that's the energy equation and the first very early simplified form. Now, you notice that this is a derivative for 2 terms multiplied together. So you have to use the multiplication rule when you do the differentiation, right? So this would be partial rho by partial t multiplied by this term plus rho multiplied by partial t of the bracket here. Then you do the same in here. Now we have 3 components multiplied together. So once you will have rho out, then you get the first derivative of the u relative to the x, fixing that bracket, and do the vice versa. So it's really, really super complicated math in here. So I will show you one term, and let's go from there. Then we can actually present the final form of this equation. So I will take these 2 components together. I will bring this to the left-hand side. So this and this will be plus, and I will keep that for now. So I will do the first simplification here. Partial by partial t rho e plus v squared over 2 plus partial rho u e plus v squared over 2, that's totally by partial x, plus partial rho v multiplied by e plus v squared over 2 by partial y plus partial rho w e plus v squared over 2 by partial z. Remember, each one of these terms is multiplied by dx, dy, dz, which is make it cancel out of the whole equation. So I'm just bringing that term to the right, to the left-hand side, so it becomes positive. I want to see how to simplify this term here. So let's assume that I'm going to take e plus v squared over 2 as fixed for now. Then I'm going to change that term. So I'm going to have e plus v squared over 2. So I should have partial rho by partial t, right? What are you going to do with this? I can take rho u. I will take e plus v squared over 2 as fixed for the first time. So this will be broken. So this is one term of the 2. The second term will be rho, right? This should be rho plus multiplied by partial t e plus v squared over 2. So this is the multiplication rule of differentiation. I took that as constant. I differentiated rho. Then I took rho as a constant. Then I differentiated this. So these 2 here is just a breakdown of this term here. Now, what about this term? I can take rho u as one bulk here. So I can do the following. I can take e plus v squared over 2 as constant. Then I will have partial rho u by partial x plus I will have rho u and I have partial by partial x for E plus V squared over 2. So these two terms here is a breakdown of this guy. Here, I will have E plus V squared over 2 partial rho V by partial Y plus rho V partial E plus V squared over 2 by partial Y. Two terms for this one. And the last one is, remember, we have plus in between, plus this will give me E plus V squared over 2 partial rho W by partial Z plus rho W partial E plus V squared over 2 by partial T. So now, if I collect the terms, I should have something like this. Remember, we only took these two terms. I bring this to the left-hand side. I took these two terms, and I'm breaking it down. I didn't deal with this. I didn't deal with this or these terms here. So let's look into this. I can collect the terms here, so I will have the following. I can take E plus V squared over 2 as a common factor. What we're going to have? I will have, from this term, partial rho by partial T. From this term, I will have partial rho U by partial X. From this term, I will have partial rho V by partial Y. Plus, from this term, I will have partial rho W by partial Z. This is by taking this common factor here. From the second term, I will take rho as a common factor. So what you're going to get, I will have, remember, these two added terms. So I will take only partial E by partial time T plus rho is here, partial E by partial time T, that's here. For this term, I will have rho is outside. Then I will have partial E by partial X, but there is U outside. So I will have U partial E by partial X plus there is V partial E by partial Y plus W partial E by partial Z. Let's see what's the remaining term here. I will have rho partial V squared over 2 by partial T. So it's partial V squared over 2 by partial T plus partial V squared, and there is U as well. So it will be U partial V squared over 2 by partial X plus V partial V squared over 2 by partial Y plus W partial V squared over 2 by partial Z. So this two terms they became like three terms here. So let's see now. What is this? Partial rho by partial T plus partial rho U by partial X, same V. This is a continuity equation. So this is actually equal to 0. This term is gone. Right? So I get rid of this one. So these two terms end up to be this one and this one as well. Right? So that's the remaining of that part. So let's call that step A. Now let's look to step B. I'll go back to that big equation. I will take that term here. Remember, this term here is what? It's differentiating P times U divided by partial X. So it's going to be P partial U by partial X plus U partial P by partial X, right? So first time the derivative of the second term and vice versa. So let's take that term by itself. Remember, we brought this one to the left-hand side. I'm going to keep that one as is, but let's see how we're going to break the pressure by itself. So I'm going to take partial PU by partial X plus partial PV by partial Y plus partial PW by partial Z. This will be the following. This one will give me P partial U by partial X plus U partial P by partial X. These two terms is the breakdown of this guy, plus P partial V by partial Y plus V partial P by partial Y. Two terms for this one, plus P plus partial W by partial Z plus, sorry, that's P times partial W by partial Z plus W partial P by partial Z. So I can simply collect the terms here at the following: P, 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 so that's P. Then I have multiplied by partial U by partial X, partial V by partial Y, partial W by partial Z. What is this? This is actually nabla dot V. Plus, the remaining terms are U partial P by partial X, plus V partial P by partial Y, plus W partial P by partial Z. So I break down these three values of the pressure into 1 and 3. That's 4 terms here. So that's the second term. Now it's the time to go for the stress term, which is go back to the original equation. I finished D3. Now I'm going to go for the stresses, the 3 terms for the stresses, and see how we're going to break them down. So let's get the normal stress term and see how we can break it down or simplify it. So I'm going to copy that term. I'm going to call that C, partial sigma x u by partial x plus partial sigma y v by partial y plus sigma partial sigma z times w by partial z. So again, remember, this is the multiplication rule. If you want to make the differentiation here, you're going to break down into the following. So this term will be u partial sigma x by partial x plus sigma x partial u by partial x. So we break down that term into 2 terms here. Do the same here. I will have v partial sigma y partial y plus sigma y partial v partial y. I do the same for the third term. That's going to be w partial sigma zz by partial z plus sigma zz partial w by partial z. If I rearrange the equation, it will be u partial sigma x by partial x plus v partial sigma y partial y plus w partial sigma zz by partial z plus sigma x partial u by partial x plus sigma y partial v partial y plus sigma zz partial w by partial z. So this is a breakdown of the normal stress term. Now the last 6 terms is 1, 2, 3, 4, 5, 6 that came from the shear stress. Then you have to take each one of them, then you break it down into 2 terms. So these will lead to a 12th term. V is fixed, you differentiate that, then you fix this and differentiate that. Roughly, let's do that here. So if I take that partial tau x y v by partial x, this will be, let's call that actually d here. This will give me the following. So I'm taking that term here. This will give you equal to v partial tau xy by partial x plus tau xy partial v by partial x. Then you break down the second one here. You break down the third one here. 4th, 5th, and 6th. You break all of them. Then you can also use, so you're going to break, let me write it down. So it's partial tau xz w by partial x will be w partial tau xz by partial x plus w, tau x z partial w by partial x. Take the third term, partial tau yxu by partial y. This will be u partial tau yx by partial y plus tau yx partial u by partial y. Then partial number 4, tau yzw by partial y will be w partial tau yz by partial y plus tau yz partial w by partial y. Then I take the last two terms here, partial tau xzu by partial z would be u partial tau zx by partial z plus tau xz partial u by partial z. The last term is partial tau zyv by partial z would be v partial tau zy by partial z plus tau zy partial v by partial z. So this is the breakdown of these 6 terms. In addition to that, we're gonna use that tau is equal actually mu partial u by partial y. That's tau in the u direction, right? Then you do that breakdown and you collect all the terms, you should reach the final form of the equation. In addition to that, actually, you're gonna use x, y, and z momentum equations to be able to reshape all these. It's gonna take like maybe a full day to do that, but I'm just giving you the major steps to do that to drive the energy equation. Then when you collect the terms, you should end up having, you're gonna get A, B, C, D into the main equation. You're gonna end up having the following equation, which is the most close form to the energy equation, which is rho partial E by partial T plus U partial E by partial X plus V partial E by partial Y plus W partial E by partial Z equal to partial by partial X lambda partial T by partial X plus partial by partial Y lambda partial T by partial Y plus partial by partial Z lambda partial T by partial Z plus minus P times nabla dot V plus the body force, the heat source, the volumetric heat generation source, plus mu times phi. So this is the equation that you're going to get. Then phi, it's called the dissipation function. And phi will collect all these stress terms. So you'll find that phi is equal to 2 partial u by partial x square plus partial v by partial y square plus partial w by partial z square plus partial v by partial x plus partial u by partial y square plus partial v by partial z plus partial w by partial y square plus partial u by partial z plus partial w by partial x square, then minus 2/3 of partial u by partial x plus partial v by partial y plus partial w by partial z. This is phi that's collect all the terms that came from the stress. So To generalize that equation, I can write it as the following: the total derivative of rho E relative to the time t, which you can break it into two terms, which is partial rho E by partial t plus u partial rho E by partial x. Please go back to the total derivative definition, plus v partial rho E by partial y plus w partial rho E by partial z. So this is a definition. I can collect that term here and write it down by d rho E by dt. Then this term here, this is nabla dot lambda nabla t, right? So these terms can be collected in very simple shape here. So nabla dot lambda nabla t is simply, nabla is partial by partial x dot this term, which is lambda partial t by partial x, and you add up the same for the y. And you do the same for the z. Then that energy equation can be simply written as g rho E by dt, which is, this is partial rho E by partial t, right? Actually, that's going to equal to nabla dot lambda nabla t, this is this term, minus p nabla dot v plus rho q dot s plus k dot v plus mu phi. And I will say this is the final form of the energy equation that we were looking for. Remember, this term can be written into two terms here, right? This is partial rho E by partial t, right? And this can be combined into there is v dot v, that's uv w dot the nabla rho E, right? Nabla rho E, or you can write it down as nabla dot rho E v, right? Either way here. Then, if you are dealing with incompressible, you know that rho is going to come out of the equation, right? So rho will get out. If you are solving inviscid flow, this means that mu will come out, right? Mu will be constant. Mu is exist. Okay, mu will be show up in the energy term. Remember, E is simply the internal energy, right? So let's write down the special cases here. So if I'm dealing with incompressible flow, incompressible, so it will be rho partial E by partial T plus U partial E by partial X plus V partial E by partial Y plus W partial E by partial Z. So it's incompressible. Let's also assume that lambda is constant. This means that lambda here can come out, and I will have the second derivative of temperature. That I will have actually simply lambda partial 2t by partial x squared plus partial 2t by partial y squared plus partial 2t by partial z squared, which can be written as lambda delta T, or you can write it as nabla dot T, right? Nabla dot nabla T, right? Nabla dot nabla T times lambda, either one. What's next? Then the rest of the terms will remain. So that's K dot V plus rho Q dot S plus mu phi, right? Minus P nabla dot V. So what happened is rho came out of this equation and lambda came out of this equation, right? And everything else remained the same. If we are dealing with ideal gas or incompressible fluid, I'm still, E can be written as V or Cp times T, right? So I can replace E with this here, and T is actually constant, right? So if you put that in here, you'll find that the equation into be rho C partial T by partial time T plus U partial T by partial X plus V partial T by partial Y plus W partial T by partial Z. It's equal nabla dot nabla T minus P nabla dot V plus rho Q dot S plus mu phi plus what is missing is K dot V. So you can take that out here because of the constant properties. Then if you think, if we solve for diffusion only, if we are doing diffusion problem, this means that velocity vector is not required. Diffusion means that there is no motion of the bulk fluid. It's like conduction. I want to show you where that equation will go. So this means the velocity vector is gone. U, V, W is gone. V is gone out of here. Let's ignore the other terms in here. I'm going to end up having the following equation. I will have rho C partial T by partial time T equal to nabla dot lambda. Lambda is going to be constant, so it's going to be actually lambda partial 2t by partial x squared plus partial 2t by partial y squared plus partial 2t by partial z squared. Looks familiar equation here? Yeah, that's the heat diffusion equation. And the dissipation function, it's super complex, right? But you have to look to what exists of the velocity component. But again, it's very important. This cannot be ignored in most cases, except it has phi has velocity all over, and because of the diffusion, velocity was ignored, so you can reach that situation. If you are dealing with ideal gas, that's another special case here. So we know that E is actually equal to CVT and H is equal CPT. So keep that in mind. But also we can add the equation of the state here. So it's PV equal RT, right? So H, the enthalpy, is the internal energy plus RT. Actually, H is equal E plus PV. PV can be replaced by RT and E can be replaced by CT, right? This is CPT, that's H, right? And this equal E plus RT. Okay, and also we can have H equal E plus P over rho, right? Remember from the ideal gas, P can be written as rho RT. Again, this is just a different combination of the ideal gas properties here in case you need to replace E in this equation by a function of H or T or whatever it's needed if you want to implement the pressure and density change into this equation. So again, this is a general equation that we gonna use all the time, and it depends on the problem condition. We're gonna simplify the equation. So at the end, I would like to just put all the equation together. So we were able to get the partial rho by partial t plus nabla dot rho v. This equals 0. This is my continuity equation. The second equation was actually d rho v by dt, which can be written as partial rho v by partial t plus either you write v dot nabla rho v, or you can write it down as nabla dot. Let's keep it that way. Let's keep it that way here for the momentum equation, so it doesn't confuse anyone. It's equal minus nabla p plus nabla dot mu v plus rho g. That's actually the momentum equation, and you can derive out of it the x momentum, y momentum, and z momentum. So this is going to be 3 equations, and this is 1 equation. And the last one is the energy equation, which is d rho e by dt, which is simply partial rho e by partial time t plus nabla dot rho e v, or it's v dot nabla rho e, but I prefer the first form, that equal to minus p nabla dot v plus rho q dot s plus k dot v, and the most important is mu times the dissipation function. This is the energy equation. So that's another 1 equation. We are actually study the conservation laws to calculate pressure, right? Density, temperature, U, V, and W. So we are getting the pressure, density, temperature, and the 3 components of the velocity. These are 6 equations. We have 3, 4, 5. So the missing one is actually the equation of the state, which is PV equal RT, or P equal rho RT, whatever you like to write it. So that's 1 equation. Now we end up having all the equation that's needed to solve any problem and really get the thermophysical properties and the velocity component, pressure, U, V, W, and the thermophysical properties of that flow. So these are the conservation laws. I think we were able to drive all of them. I know the energy equation is quite some hard and it's really complicated, but at least you know what's the methodology to drive this equation and how it's end up to be. And I think that's going to conclude that part of the conservation laws.